So 8.1 and 8.2 are going to be combined in one lesson. So we are going to first talk about modeling with differential equations, and this will take place with the separation of variables as well. So first of all, we're going to start with the modeling of differential equations, and a differential equation is an equation involving one or more derivatives, okay, of an unknown function. So the first thing you need to do is determine the order of a differential equation, and what that is it's the highest derivative in the equation. So what we have here are a series of derivatives, and what we're going to do is determine what their order is. And a lot of times these are written in order, but some of these are written in different ways. So first of all, we have this first differential equation, and what we're looking for is what is the highest derivative. So we're looking for what is the highest derivative. Okay, so we want the highest. So when we look here we have dy dx, okay, and the degree of dy and dx is 1, so the order here is 1. Okay, all we're trying to do is determine what the order is. So if you look here, this is actually written in standard form, and you have the second derivative here because of this degree, okay, and then you have the first, and then this is just y, this is not a derivative, so in this case the highest order would be 2. So in this case these are all written in terms of x, but remember your variable can be with respect to anything. So what we have here is dy dt, and this is the highest derivative, so this is going to be a third order. And this is pretty much in differential notation, so this is actually better when we're talking about in terms of separation of variables, which we'll get to. Prime is easier to write, but it's not beneficial when we're using separation of variables. So when you have something like this where this is y prime or y double prime, you want to actually rewrite this once we get to separation of variables. So y prime is the same thing as dy dx, and this is the highest derivative, okay? So this is a first order, okay? And then here we have y double prime, which is the highest. And remember, y double prime is d squared y over dx squared. Okay, so this is a second order. Okay, so as I stated before, the last two equations in this table are expressed in prime notation. Okay, and the independent variable is not explicit, meaning you cannot see what the independent variable is. So you actually need to be able to rewrite as dy dx or dy dt or whatever the highest order is, because it will be more beneficial when we're dealing with separation of variables. Okay, so let's take a look here at our first example, and this is just pretty much separation of variables. So it says, suppose that we have a particle moving along the s-axis in such a way that its velocity is always half of the position. So remember, s of t is our position function, and v of t is our velocity. So we need to find a differential equation whose solution is in terms of s of t. So what that means is everything needs to be in terms of the position. So what they're saying is that velocity is 1/2 the position function. So here, this is currently not in terms of the position function. So what we need to do is rewrite this in terms of the position. So remember, velocity is the first derivative of position. So you have ds dt is equal to 1/2 of the position function. And this is your answer. Okay, because it has to be written all in terms of the position. Okay, so our second example in the same one is that suppose that a particle, again, is moving along the position axis, s-axis, in such a way that its acceleration is always twice the velocity. So acceleration is always twice the velocity. we want to find a differential equation whose solution is s of t. So again, we want to rewrite this in terms of the position. So start with what they tell you. So our acceleration is twice the velocity. Okay, so in terms of the position, over here I'll say acceleration is the second derivative of position. Okay, and velocity is the first derivative of position. So now what I can do is rewrite this in terms of the position. However, don't use prime. We want a differential, which means we have to have d squared s dt squared, which is the acceleration. It's the second derivative of position, is equal to the first derivative, which is 2 ds dt. Okay, so again, this is all in terms of the position. And I know this because that's what it told me in the directions. Okay, in our last example, it says verify that the functions are solutions of the differential equation by substituting the functions into the equation. So this is a verify problem. So we want to show that this is true. And what we want to show is that the second derivative minus the first derivative minus 6 times the original function will be equal to 0. So this is going to take some time, and this is actually a two-part problem. So in the first part, what we're going to do is take a look here. We know that this is what y is equal to. So now we need to find the first derivative because we need it for the problem. So this would be negative 2. We're using the chain rule. E to the negative 2x, so it's the derivative. Then we're using this to find the second derivative. So this would be 4e to the negative 2x. So now we have all of our derivatives. So we have the second derivative here. We have the first derivative here. And we have the original, which they gave us in the beginning. And we need to make our substitution, and what we're verifying is that once we plug all this in, that it will be equal to 0. So this is, it's kind of like a proof. So let's plug in what we know. Here we want the second derivative, so this would be 4e to the negative 2x minus y prime, which is negative 2e to the negative 2x, minus 6 times e to the negative 2x. And we want to verify, does that equal 0? So this is our question right here. Okay, so in this case, subtracting a negative becomes a positive. When you combine these two, you end up with 6e to the negative 2x minus 6e to the negative 2x, and that does equal 0. Okay? So what I want you to do right now, I'm going to pause the video, and you are going to complete that with e to the 3x, and then you'll come back and take a look at the. Okay, so hopefully you've had an opportunity to complete this, and this is what we're going to look at. So first we are told that y is equal to e to the 3x. Then we had to find y prime, and then we had, using y prime, we had to find the second derivative. So then I went up here and I plugged in everything. So second derivative minus the first derivative minus the original. And I wanted to know, does that equal 0? And it does.